Rational exponents. Definition: b to the 1/n power. For the counting number n, where n does not equal 1, if n is odd, then b to the 1/n power is the number whose nth power is b, and we call b to the 1n power the nth root of b. What this means, if I have 8 to the 1/3 power, that equals 2, because 2 times 2 times 2 is 8. So we have the third root of 8. Also, if I have -8 to the 1/3 power, that's -2. If n is even and b is greater than or equal to 0, then b to the 1/n power is the non-negative number whose nth power is b, and we call b to the 1/n power the principal nth root of b. If I have 25 to the 1/2 power, that's 5, because 5 times 5 is 25. 5 is the principal square root of 25. If n is even and b is less than 0, then b to the 1/n power is not a real number. If I have -49 to the 1/2 power, that answer is not a real number. 7 times 7 gives us a positive 49. -7 times -7 also gives us a positive 49. There's not a number times itself that will give us a -49. b to the 1/n power may be represented by the nth root of b. If I have 16 to the 1/4, I can write that as the fourth root of 16. In these examples, I want to simplify the rational exponents. For a, I have 16 to the 1/2. That's the same as the square root of 16, so my answer is 4. For b, I have parentheses -9 to the 1/2, so my base is -9. Since the denominator of my exponent is even, this one can't be done. My answer, not a real number. For part C, I have -16 to the 1/4 power. 16 is the base. The negative is not included in the base, so we can work this one. This is similar to if I had x minus 16 to the 1/4. The minus sign doesn't come into effect until I'm ready to subtract, so the answer would be negative. 16 to the 1/4 power is 2, so my answer is -2. In this example, we still want to simplify. A, I have 32 to the 1/5 power. That simplifies to 2. For B, I have parenthesis -27 to the 1/3 power. The third root of 27 is 3, and since my denominator is odd, I can work -27. That gives us a -3. Part C, I have 64 to the -1/3 power. First thing I have to do is get rid of the negative in my exponent. That gives us 1 over 64 to the 1/3 power. The third root of 64 is 4, so my answer is 1/4. Rational exponents. The definition of a rational exponent: for the counting numbers m and n, where n does not equal 1, and b is any real number for which b to the 1/n power is a real number, b to the m/n power equals b to the 1/n power to the m power, or b to the m power to the 1/n power. So what this means is if I have 4 to the 3/2 power, I can write that as 4 to the 1/2 power cubed, or I can write that as 4 to the 3rd power to the 1/2 power. To solve this, it would be easier to use the 4 to the 1/2 to the third power, because 4 to the 1/2 is 2, and 2 cubed is 8. b to the negative m over n power is equal to 1 over b to the positive m over n power, where b does not equal 0. A power of the form b to the m over n, or b to the negative m over n, is said to have a rational exponent. So as always, we can get rid of the negative exponent by flipping it. In this example, we want to simplify the following. Let's start with a, 25 to the 3 over 2 power. First, let's separate our exponent, 25 to the 1/2 power to the third power. 25 to the 1/2 power is 5. 5 cubed is 125. For b, we have negative 125 to the 4/3 power. Since our denominator is odd, we can work this one. Let's split them up into negative 125 to the 1/3 power to the 4th power. The cube root of negative 125 is negative 5. Negative 5 to the 4th power is negative 625. In part C, we have 8 to the 5/3 power. Splitting that up, we have 8 to the 1/3 to the 5th power. 8 to the 1/3 power is 2, and 2 to the 5th power is 32. For our next example, we want to simplify 9 to the negative 3 over 2 power. Because my exponent is negative, I need to change this to a fraction. I have 1 over 9 to the negative 3 over 2. Splitting up my exponent, I have 1 over 9 to the 1/2 to the third power. 9 to the 1/2 is 3, so we have 1 over 3 cubed, which becomes 1 over 27. For b, we have 8b to the third, all to the 4/3 power. Both the 8 and the b to the third are to the 4/3 power. So splitting that up, we have 8 to the 4/3 power, which I've split up into 8 to the 1/3 to the 4th power. And then we have b to the third to the 4/3 power, which is split up b to the third to the 1/3 to the 4th power. 8 to the 1/3 power is 2, so I have 2 to the 4th. b to the 1/3 power becomes 3 over 3, which is 1. So now I just have b to the 4th power. So my final answer is 16b to the 4th. In this example, we want to simplify b to the negative 4/3 over c to the 1/2 times b to the negative 2/3 times c to the negative 3 over 2. My first step is to combine the b's and combine the c's. Since I'm multiplying the variables, I can add the exponents. So I have b equals negative 4/3 plus negative 2/3 times c to the 1/2 plus the negative 3 over 2. Negative 4/3 plus negative 2/3 will give us negative 6/3, so I have b to the negative 6 over 3. 1/2 plus a negative 3 over 2 gives us a negative 2 over 2, so I have c to the negative 2 over 2 power. Those powers reduce to b to the negative 2, c to the negative 1. I need to have positive exponents. 1 over b squared c is my final answer. In this example, I need to simplify b to the 3/4 c to the 1/2 divided by b to the negative 1/4 c to the negative 1/2. Since I'm dividing my variables, I subtract the exponents, which gives me b to the 3/4 minus the negative 1/4, c to the 1/2 minus negative 1/2. 3/4 minus 1/4 becomes 4 over 4, and 1/2 minus the negative 1/2 becomes 2 over 2. So I have b to the 4 over 4 times c to the 2 over 2, which reduces to b times c. In this example, I want to simplify parentheses 27b to the 1/3 c to the 3/4 over 8b to the negative 2/3 c to the 1/2, all to the 4/3 power. By order of operations, we need to simplify what is in the parentheses first. So this gives us 27 over 8 times b to the 1/3 minus a negative 2/3, c to the power 3/4 minus 1/2. And all of that is still to the 4/3 power. Simplifying, I have 27 over 8 and then b to the 3 over 3 because 1/3 minus a negative 2/3 is actually 1/3 plus 2/3, which is 3 over 3. And then c to the 1/4, I have 3/4 minus 1/2, which is the same as 3/4 minus 2 over 4, which gives us 1 over 4. And all of that is still to the 4/3 power. So I have 27 to the 4/3 power divided by 8 to the 4/3 power times b to the first times 4/3 times c to the 1/4 times 4/3. For the 27 and 8, I need to split up my exponent so that I can solve it. For b and c, I can just multiply the exponents. So I have 27 to the 1/3 to the 4th power and 8 to the 1/3 to the 4th power. 1 times 4/3 is just 4/3, so I now have b to the 4/3 power. 1 over 4 times 4 over 3 is 4 over 12, which reduces to 1/3, so I have c to the 1/3 power. 27 to the 1/3 power is 3, so I now have 3 to the 4th. 8 to the 1/3 power is 2, so I have 2 to the 4th. b to the 4/3 times c to the 1/3, because I'm done with that math. 3 to the 4th is 81. 2 to the 4th is 16. Final answer, 81 over 16, b to the 4/3, c to the 1/3. In this example, we want to find the following for f of x equals 2 parentheses 27 to the x power. We're going to find f to the 2/3. Again, we have function notation. Writing the f to the 2/3 is important. We want to replace x with 2/3. So we have 2 parentheses 27 to the 2/3. Only the 27 is to the 2/3 power. Splitting up our exponent, we have 2 parentheses 27 to the 1/3 squared. 27 to the 1/3 power is 3. So we have 2 times 3 squared. 3 squared is 9. 2 times 9 is 18. So for an input of 2/3, we have an output of 18. In this example, we're going to use the same function, f of x, and we're going to find f of negative 1/3. Replacing x with 1/3, I have 2 times 27 to the negative 1/3. 2 has an exponent of 1, which is positive. 27 has an exponent of negative 1/3, which means I need to flip the 27 to the negative 1/3. I have 2 times 1 over 27 to the 1/3. Since the third root of 27 is 3, I now have 2 times 1/3, which is just 2/3. In this example, the amount in megawatts of new solar power installed in the United States are shown in the Table 8 for various years. The year 2006, the amount of new solar power installed in megawatts, 105. 2007, 160. 2008, 290. 2009, 435. 2010, 878. 2011, 1,891. 2012, 3,300. Source, GTM Research. Let A be the amount in megawatts of the new solar power installed in the year that is T years since 2000. The situation can be described by the linear function A equals 486.96 T plus 3,374.25 and the exponential function A equals 2.73 parentheses 1.8 to the T power. Part A. Use a graphing calculator to draw the graphs of the two functions and, in the same viewing window, the scattergram of the data. Which function describes the situation better? So going back to our data, if we're looking at T years since 2000, our 2006 becomes 6, 2007 becomes 7, 2008 becomes 8, 2009 becomes 9, 2010 becomes 10, 2011 becomes 11, 2012 becomes 12. And then we just have our values for A. On our calculator, we're going to use T as our L1 and A as our L2. Let's begin by graphing our data points. So stat and then enter. Make sure you're under L1 and we'll type our data for T, 6, 7, 8, 9, 10, 11, 12. Go over to L2 and then type the data for A, 105, 160, 290, 435, 878, 1,891, 3,300. Our next step is to type in our equations. Y equals 486.96 and then our variable minus 3,374.25. Enter. And then our exponential function 2.73 parenthesis 1.8 to the t power. It's going to always show up as x on here. I can tell from here that I don't have my plot on because that would be highlighted in black. Second, y equals takes us to our stat plot. I'm going to press enter and then enter to turn it on. From here, we want to press zoom. We want zoom stat, press 9. The blue line, of course, is our linear function, and the green line is the exponential function. So which graph fits the situation better? The exponential function, a equals 2.73 parentheses 1.8 to the t power. Part B. Use the exponential model to predict the amount of solar power that will be installed in 2018. Since we're starting with the year 2000, 2018 take away 2000 is 18. Using our exponential model, a equals 2.73 parentheses 1.8 to the t power, we're going to let t equal 18. So that gives us a equals 2.73 parentheses 1.8 to the 18th power. So we need to calculate that. So second quit gets me back to my main screen. And then I'm ready to type in my function, 2.73 parenthesis 1.8 parenthesis rooftop for exponent 18. Enter. So our result is 107,415.694. Rounding to the nearest megawatt, my final answer is 107,416 megawatts. Part C. Use the exponential model and intersect on a graphing calculator to predict in which year the amount of solar power installed will be 30,000 megawatts, the equivalent of more than 24 nuclear power plants. We can use intersect if we let y equal 30,000. Moving to our calculator, we want to go to y equals. Since our model didn't fit the linear equation in y1, we can get rid of that, clear, and put our y equals 30,000 there. Now we're ready to graph. If you can't see where they intersect, go to Window, change your X max to 20 and your Y max to 35,000. In order to use intersect, we have to see where the two lines cross on the calculator screen. Using that max for your x and for your y should allow you to see where they cross. Intersect is in the Calc menu. Second, Trace. Intersect is 5. I can just press Enter 3 times. And we get our intersection. When x is 15.82998, y will be 3000. So if x is 15.8, rounding to the nearest year, that's going to be 16. Since we're starting in the year 2000, my answer will be 2016. 2016 will be the year that we predict we will have 30,000 megawatts in solar power. Rational exponents. Rational exponents can be written in the form of b to the 1/nth power instead of writing it as a root. If I have b to the m over n power, I can always rewrite that as b to the 1/nth to the m power. If my exponent is negative, I put it in the bottom of a fraction to make it positive. All the properties of exponents apply when you're using rational exponents.